Okay, welcome everyone. I hope you're all having a good day. My name is Juliana Lisi, and I'm Sustainability and SAF Manager for C-SAF for the Canadian Council for Sustainable Aviation Fuels. I'll be your host today, and welcome to Fueling SAF Knowledge, SAF Feedstocks, and Sustainability. And I actually saw this morning that today is World Sustainability Day, so I find it very appropriate that we're having this webinar. This webinar is being recorded, so if ever you want to catch up, if you have to step away for a second, we'll make it available to all the attendees, and we'll also post it on our website. In case you didn't know, we also have a webinar tomorrow, same time online. I will post the link to that one in case you want to register for that one as well. I will post it in the chat. The way we are going to function today is essentially I will be giving a short introduction on C-SAF and what we do. Then I will have our speaker, Susan Van Dyke, give her presentation, and then we'll leave some few minutes at the end for some Q&A. Yes, so as I mentioned, we are C-SAF, and back in 2021, the Canadian airline operators who own the fueling infrastructure at the major airports across Canada noticed that there was no single point of contact for SAF here. So in February of 2022, they launched C-SAF. And essentially, we also have a membership, which consists of companies who we think would be involved in creating a SAF production for Canada. So that means we have fuel refiners, we have airports, we have technology, OEMs. We've really tried to gather who we think could help us in our venture. So our mission is simple but ambitious. We want to get SAF production going in Canada. And in June of 2023, we released a roadmap showing that we put in an aspirational target of 1 billion liters by 2030 for SAF use and SAF production here in Canada. And I can show you a little bit more on that later on. So how do we get there? So one of the ways that we intend to do so is basically influencing policy. So we call it our SAF policy North Star, and it essentially consists of these 4 pillars. So the first one, reducing aviation emissions. All aviation industry reports that have come out lately are essentially saying the same thing. We will need SAF in order to reach net zero goals for aviation. That is just the facts. And our second pillar is basically we want to make SAF here in Canada. We feel that we have all the right ingredients in order to do so. Our third pillar is basically keeping the sector competitive. We know that SAF can be up to 2 to 5 times more expensive than regular jet fuel. And obviously, the airline companies do not want to pass on those costs into their airline consumers. So we want to make sure that the pricing for SAF stays competitive. And then finally, we want to activate Canadian feedstocks. And that includes all the feedstocks that we have available here in Canada. We will need them all in order to get to the volumes that we want. So that means forest residues, agricultural residues, e-fuels, all of those will be needed in order to reach our goals. Okay, so if we go under our work, we have a few documents here that might interest you. So I mentioned before the SAF roadmap. This was published in June of 2023, and essentially it lays out the steps that we need to take now in order to reach that 1 billion liter goal by 2030. So if you're interested in seeing that one, that is that one there. Some of our new documentation would be under SAF briefing reports. So if you click on this one, we've come out with a few I would say, technical briefs that basically deal with everything touching SAF related with a Canadian context. So you can just click on, one of the pictures here, whichever topics that interest you, and that'll take you to a landing page that basically, if you scroll down, you can click here and download the report. If you're interested in all of them, you can do that as well. You can have all of them available to you. Again, you just scroll down here, type in your email, click access the briefs, and you will have those available as well. And then finally, again, under our work, we have impact reports. These are economic impact reports that we will be putting on this tab here. We have our first one, which is essentially a Canadian-wide economic impact report. Again, you can just fill in your information here and it will be available for download. We will have also a BC one coming up that will be placed here as well within, I would say, maybe the next month or so. So that's, and then, just for your information, we also have the Join the SAF Community link here. And that is our SAF community that you can join. And it basically gives you access to resources, news, events, and essentially you can get in contact with people here as well. So that's all I wanted to mention for the website. And now I will go ahead and present Susan Van Dyke, who is our speaker today. Susan is an expert in the field of sustainable aviation fuels and biofuels with 18 years experience. Her expertise includes an in-depth understanding of the technologies for SAF production, their potential and challenges, and research and commercialization trends. She is the author of and co-author of numerous influential reports focusing on the application of biofuels and SAF in transportation sectors. She has worked on several SAF projects funded by Boeing, and she acts as a reviewer for the US Department of Energy. Other clients include Pratt & Whitney Canada, Deloitte, ICF, and ourselves, C-SAF. She recently completed a feasibility on SAF in India for ICAO. Susan holds a doctorate in biochemistry and a master's degree in law. She works as a consultant and also as a research associate at the University of British Columbia. So
Thanks,
Susan,
Juliana.
I will, thanks, you can go right ahead.
Thank you to C-SAF for asking me to speak here today. And I'm going to share some interesting information today on feedstocks and sustainability, and tomorrow specifically looking at technologies and the supply chain and certification. So today what I will specifically look at is feedstocks in Canada, oils and fats, forest residues, agricultural residues, and municipal solid waste, availability and distribution, challenges and opportunities, and then looking at the sustainability, only focusing on CORSIA. So when we look at the feedstocks in Canada and availability, we have to just be aware that we can't just look at theoretical availability, but also have to consider technical availability, the cost of the feedstock, which will impact its economic availability, and also what is competition for the use of these feedstocks. And specifically, when we look at the energy density of feedstocks, this impacts the regional availability and considerations. We know that in Canada, most of our feedstock is forest residues, agricultural residues, MSW, but the problem is that it's a low energy density feedstock with moisture content, oxygen, and not economical to transport more than about 100 kilometers from a SAF facility. So we are likely to see SAF production located closer to feedstocks unless we can develop a distributed, or what they call a depot supply chain, based on densified feedstocks such as wood pellets, or yeah, even bio oils, and so on. We don't have this problem with high energy density feedstocks such as canola oil or used cooking oil or even ethanol, because there are established supply chains over long distances that are already in place, and therefore we can sort of piggyback on those existing supply chains. And it's economical because it's a high energy density feedstock, but also because of optimized supply chains. And the high energy density feedstocks allow the location of the SAF facility to be anywhere and usually closer to the supply chain. So just looking at oils and fats availability in Canada, from a vegetable oil perspective, we have canola and soybean oil, and then waste, we have used cooking oil and tallow. So the tallow specifically, there are 14 rendering facilities in Canada that handle over 3 million tons of raw materials every year. Used cooking oil, there's not a lot of information on specific availability. Then we also have tall oil, specifically relevant because it's produced as part of the kraft wood pulp process. So it's not separated by all kraft pulp facilities. In some cases, it's just burnt as part of the energy generation. But in Sweden and Finland, it is separated, and it forms the feedstock for companies such as Preem, and they make renewable diesel since 2010 based on this feedstock. So if we can't keep our feedstocks domestically, exports will impact it, and this will depend also on policy and market price, for example, demand in the EU, incentives, and so on. And currently, we already see that UCO, tallow, and canola are exported quite extensively, and in 2023, inedible oils and fats exports amounted to about 276,000 tons. So yes, creating the SAF ecosystem within Canada to drive the use of these feedstocks domestically is critical. So when we just look at vegetable oil feedstocks, we have canola and growing regions and soybean growing regions. Canola is the more prominent feedstock that we will be considering, and availability. Here are some numbers just for those two types of feedstocks. So we have oilseed production, then we have the crush capacity, which gives us the vegetable oil production, and then oil and oil seeds are exported. So when we look at canola, for example, not all the seed is crushed in Canada, and a big part of the oil seed volumes are actually exported. And if we want to increase domestic availability, increasing the number of crushing facilities could do that. And most exports are to the US and then also to China. But of course, there are all these tariff issues and policy issues impacting the market at the moment. Sorry, just trying to. Okay, so here are canola oilseed crushing facilities, and although there is already a large volume of crushing taking place, I think expanding crushing facilities could be a key factor for increasing SAF feedstocks from this canola. Then if we look at the other major type of feedstock in Canada, forest residues is obviously a big part. If we look at forest residues, these are in-forest residues, sawmill residues, and urban wood waste. And of course, the difference is that sawmill residues are produced near the sawmills, and therefore is a more accessible or low-hanging fruit feedstock, and then agricultural residues as well. So this is really the primary types of feedstocks that we have available. And of course, it's not the feedstock availability that's the issue. It's implementing the technologies that can use them and commercializing them, and then optimizing the supply chains to ensure the economic viability of feedstock pricing. So when we look at forest residues, uh, this is mostly linked to logging, but often the residues are generated in remote locations far from existing supply chains. And this will require establishment of new supply chains, particularly because it's not worth bringing residues out of the forest unless there are specific policies and practices put in place. So as we can see, the forest residues are generated from logging. The logs are removed, but the residues stay behind in the forest. And then we have the second category, which is the sawmill residues, where we have hog fuel shavings, sawdust, and wood chips. Wood chips are obviously used for pulp, but sawdust shavings and hog fuel can be used in areas such as BC. Most and or if not all of the residues at the sawmill is already used for wood pellet production, and probably in Quebec area as well, Quebec, Ontario. So companies there are starting to look at using residues. To some extent, they've started doing that. But of course, then it becomes a lot more expensive to access the feedstock, and the quality is also reduced. So the difference in cost is that you don't have to transport the sawdust and shavings from the out of the forest. So it's cheaper. It's already size reduced, and therefore it's quite ideal. But there are limited volumes, and it's all dependent on the entire logging sector. Using residues has in forest residues has a lot of opportunity and potential because it will avoid emissions from burning, but then you have increased cost of chipping, drying, grinding, transport, and you also have a quality issue because you're more likely to get mud and so on. And the other issue is it reduces the carbon intensity because all of these additional processes and transportation will add emissions. So the wood pellet sector is is a huge opportunity for SAF production, provided we can overcome the cost issue to identify whether it can be economical. The sawmill residues are already used extensively, and Canadian producers manufacture about 3.45 million metric tons of wood pellets, and that was in 2023, about 45 producers. So this is really an ideal feedstock from a gasification point of view, not for all gasifiers, but it's a consistent size, it's dry, and it has a low ash content. So it's actually a really great feedstock for gasification. And as you can see, BC, Ontario, and Quebec has the majority of the wood pellets that are currently produced. The big thing is, of course, the cost of the wood pellets. So if using only residues, it's very sustainable. There is some use of low quality logs and that kind of thing. The sustainability of that is still qualified under or described under the CORSIA methodology. But what is important is that the wood pellets can support large-scale facilities that are more economical for technologies such as gasification. So it can support a distributed supply chain model where you have a transport of the wood pellets with existing supply chains already in place, and then a centrally located gasification facility that can use that. So currently, most wood pellets are exported specifically to the UK and Japan, and there's a lot of it is driven by policy, say in the UK, because it's used there for electricity production by Drax, and Drax also owns a number of facilities in BC. But if these residues and wood pellets can be utilized within Canada, that could, of course, be very beneficial. The big problem is the issue of cost. There are fluctuating costs depending also on the grade of the quality and grade of the wood pellet prices. But just recently looking at the ICAO SAF rules of thumb, when they take into account transport and grinding and size reduction, their forest residue supply, feedstock supply, comes at about estimated $180 per ton. So I think looking more into whether the upside of having a very consistent dry feedstock with a homogeneous quality, low ash content, couldn't still be a viable opportunity for gasification. The wood pellet producers are spread across Canada. And then looking at agricultural residues, there's a lot available from harvesting. Although some straw remains on the fields and some are used for animal bedding and animal feed, the residues can be used for biofuel production. But of course, if you know anything about cellulosic ethanol production from residues over the last 12 years, there's been a number of failures of these facilities in the US and globally, and therefore it's a very challenging technology to commercialize and make it economically viable. A lot of it is to do with the characteristics of the residues, the transport, the storage, etc. So this is problematic. Also harvesting over a relatively short period and then trying to store it without degradation to supply a facility. So this is still a tricky issue, and globally it's a problem. The only place where there is cellulosic ethanol production on a consistent basis on a commercial scale is Raízen in Brazil, and that's because they use bagasse, which, similar to sawmill residues, is available in an aggregated form at a sugar mill, and therefore is considered the low-hanging fruit for, but of course we don't have that. When it comes to ag residues and pelleting and whether that could be a potential way to get the feedstock supply chain going, the problem is that the lower lignin content in agricultural residues means that additives are required to create the pellet, and these actually will interfere with enzymatic processes for cellulosic ethanol production. So there's still a long way to go to solve the ag residue and cellulosic ethanol problem, unless we can utilize it in pyrolysis or gasification types of technologies, and then the scale, similarly to forest residues, become a problem. So usually reports that look at availability consider biochemical pathways to produce ethanol, which can be converted. But this is challenging and is still going to remain challenging on a commercial level for quite some time. The cost of this ethanol is also a few times higher than conventional ethanol. Biogas is not often considered, but using agricultural residues combined with manure to produce biogas, you can get higher yields, and there are companies currently looking at biogas conversion into syngas into SAF. Then MSW is also globally one of the biggest volumes of feedstock available. In Canada, it's estimated about almost 10 million tons. And about 6 million tons is biogenic content, which of course improves the carbon intensity. But again, the technologies have been very challenging. The gasification Fischer-Tropsch so far has not been successful. Enerchem had some success at demonstration scale in Edmonton for production of methanol, but we are still waiting for this technology to be demonstrated in order to use these residues. Sort of subcategories of MSW that has more potential in the sense that if you look at end-of-life tires and fast pyrolysis, this is undergoing ASTM certification. And the chemist, from a chemistry point of view, it doesn't have the oxygen problems of biomass, and there is biogenic content from the natural rubber that is used, and unrecyclable plastics with pyrolysis and co-processing, although this is not really going to give you any carbon intensity reduction under CORSIA because it will just be considered 100% fossil-based carbon. So the biggest challenge here is the quality and the contaminants, and this has not been resolved, but feedstock challenges will remain a challenge for the technology commercialization itself. Another route to utilize MSW is, of course, capping existing landfills, collecting methane that can then be used for SAF potentially. So also if we then switch to e-fuel production, obviously there's almost unlimited potential if you look at CO2 from the air, but that is the most expensive. So looking at this from a more, what is the low-hanging fruit, what are the potentials for Canada, there are abundant industrial sources such as steel, aluminum, cement production, and these are considered unavoidable. Then there are also refinery emissions. So there are a number of ways that this can be used. The biogenic CO2 from ethanol is a different source. Also, waste to energy, biomass to energy plants, if the CO2 can be collected. The challenge there is that smaller quantities of CO2 are produced. And if you want a better economies of scale, you need to find a way to aggregate the biogenic CO2 by transportation through pipelines and so on, which in Northern America, there is a lot of pipelines already because of carbon capture and storage, and these can potentially be utilized as well. The other route to use the CO2, which I didn't list here, is the potential for waste gas fermentation, the LanzaTech process for production of ethanol, and then using that in an ethanol to jet kind of process. So on the one hand, we have CO2, and on the other hand, we need hydrogen. And that really, the carbon intensity, the big issue is where does the electricity come from? Because the lowest carbon intensity will be from green hydrogen, but with methane capture of steam methane reforming, you can produce the blue hydrogen and get a SAF with a poorer carbon intensity, but could still be a useful source of hydrogen. And there's a big difference in terms of regional electricity supply and carbon intensities. But then there's also the bigger question of, is there enough electricity available to first decarbonize the grid, which is a more efficient way of decarbonization before we look at liquid hydrocarbon fuel production. So if we look just at the impact of electricity, in Canada specifically, there's a different CI score for each province for the electricity grid, which is provided in the ECCC methodology. And of course, you'll have better mitigation potential in provinces with renewable electricity. And in the EU and UK, there's also very strict regulations on additionality. And in the long term, companies who want to make e-SAF will have to show the direct link between the production of the renewable electricity on an hourly basis and the production of the hydrogen. Here is just a quick snapshot of the carbon intensity of electricity in Canadian provinces, which will give you an indication of the more suitable provinces for making e-fuels. So just to switch to sustainability, are we still on time, Juliana?
Yes, we're good, thanks.
Okay, good. So just looking at sustainability, obviously the overarching goal for making SAF is sustainability, because we have climate targets and we're looking for emission reductions. So the carbon intensity of the SAF is critical to achieve those targets, with feedstocks really having the biggest contribution to the carbon intensity in most cases. Although the broader sustainability in terms of, other criteria are critical, often we just calculate the carbon intensity because it's more quantitative, but on the basis that we understand that broader sustainability criteria must be met. Specifically, we're looking just at CORSIA criteria. So although there are multiple definitions of sustainability, multiple types of organizations looking at sustainability, here we are only concerned with what CORSIA it regulates. So CORSIA calls it eligible fuels, and they define specifically what sustainability means, and they also define how the carbon intensity must be calculated. CORSIA has a whole document on default carbon intensity pathways for feedstocks and technologies, and this is updated and published periodically, and it has a core value, which is really the life cycle from feedstock to fuel production, and then the induced land use change, which is a separate method for calculation. And if you think that you can achieve a better core value because you have implemented different steps and that reduce your carbon intensity, there is a methodology to calculate actual carbon intensity, which will then give you a lower carbon intensity SAF. But this has to be done using the CORSIA method, and the sustainability must be verified through approved sustainability verification schemes under CORSIA. So currently there are only 3 schemes that are approved under CORSIA. We have ISCC, RSB, and this Japanese company called Class NK. So they are critical. And then if we look at what is our life cycle assessment, most of you will probably know that. So it's really adding up all the emissions associated with the entire process from feedstock production through to the technology and the fuel production. And all of this has to be added up based on the data, some data from the actual process, the primary data, and then secondary data, which is, for example, what is the emissions associated with fertilizer production, etc. And under CORSIA specifically, the baseline is 89 grams of CO2 per megajoule, or CO2 equivalent per megajoule, and this is what is used to compare the carbon intensity reduction. And here is just an illustration, and all credit to Don O'Connor, who developed this diagram. And just if we look at canola specifically, all of these emissions are included from the fertilizer chemicals, the farming, the feedstock transportation. Now, at the crushing stage, we produce 2 co-products, the canola meal and the canola oil. And at this stage, all the emissions up to there are split between these 2. And according to CORSIA, that's done on an energy basis. And this is also similar to the ECCC model, and there is quite a big difference when you use energy basis or mass basis, because your SAF will have a lower intensity if you use a mass basis than if you use the energy basis. But for purposes of CORSIA, only the energy value is used, the energy content. So then you produce your SAF this way. So as I mentioned, you have under the CORSIA method, you have the default versus actual values. You have a core value and you have an ILOC value, and you can calculate an actual carbon intensity. So just to note that there's regular updates, and the most recent version from 2025 has a lot of additions, and here I've provided the links to both the default and to the LCA methodology, and you will see there's a lot of updates and differences, new pathways added. And here, just to specifically show you some of the latest default values. So for used cooking oil, 13.9, but for the first time now, what CORSIA has done is they've added this. So it's 13.9, but if you produce hydrogen from coal, you have to add that. And if the process heat is produced from coal, you have to add that. So that is more realistic in terms of the electricity grid that will vary substantially. And then there's also a default value for co-processing, which is 16.7, but note that this is only for 5% co-processing in the hydrotreater or the hydrocracker. And interestingly, there is no co-processing default value for canola, and Transport Canada probably would have to apply for that to be included if we want a specific co-processing default value. If we just look at using canola in a HEFA facility, again, there we have the core value. And in the old documents, they used to have the core value and then the ILOC value and then the total. Now they've completely separated it. And now they have ILOC values, and specifically the ILOC values differentiate between different regions. So where a country feels that their ILOC value has to be different because of specific practices like farming and so on, the country itself has to apply to ICAO for creation of a new ILOC value, because this cannot be calculated by a company itself. So the problem is that when we're dealing with provincial legislation, national legislation, and international, we have issues with different models which calculate different levels of carbon intensity depending on the model, and this all becomes quite complicated. So when we look at, for example, in Canada, you have the ECCC model under the CFR, then you have the BC LCFS where they use the GH Genius model, and then you have, if you want to export either feedstock or fuel to the US, you might have the California model or the Oregon model, Washington State, or the Argonne GREET model, and it becomes really complex. Then you also have the IRA, and so there's just this proliferation of potential models. But for the purpose of CORSIA, and if airlines want to use the SAF that they buy as offset against offset obligations, of course they have to comply with CORSIA. But if a company then also wants to access incentives under any of these policies, there will have to be multiple types of life cycle assessment carried out in order to comply and show carbon intensity under these different policies, because there can be quite a lot of differences and each model requires their own analysis. So that's it. That's it from me. Any questions? And feel free afterwards, if you have questions, to contact me via email.
Thank you so much, Susan. Okay, so we do have a few questions that came in, and I'll just start in basically at how they came in, the time that they came in. So the first question we have is, what is the feedstock that yields the most SAF? And connected to that question, would one SAF process plant be able to use more than one feedstock?
Okay, so the first question is really which feedstock will produce the most SAF. So I assume you're talking about yield per ton of feedstock. Of course, the HEFA pathway using canola oil or used cooking oil, that will give you the biggest yield because there's only 11% oxygen in the oils and fats feedstocks. So therefore, you add hydrogen, you remove the oxygen, you get a really, really high yield. I think it's about 85% maybe. But with the other feedstocks, you lose during the processing, you lose yield, but also your starting carbon feedstock in terms of how much oxygen is in your ag residues, etc., etc. So if you look at gasification, Fischer-Tropsch, forest residues, you will get, I think it's about 18% yield per ton of dry wood. Ag residues, about 14% per ton of dry residues. MSW is roughly similar, but yeah, the yields are all much lower depending on the specific feedstock. And as I said, the carbon content of the feedstock is quite important. And then there was a second question. What was it?
Would one SAF process plant be able to use more than one feedstock?
Well, it depends on the feedstock itself. If you look at oils and fats feedstocks, once it's been cleaned up and the contaminants have been removed, they are virtually the same, homogeneous from a chemistry point of view. So they're not going to behave very, very differently unless you have like tall oil mixed with used cooking oil, because tall oil has different chemistry. But when it comes to other feedstocks, hardwoods will be different from softwoods, will be different from ag residues. So potentially, yes, you can use different feedstocks, but you're not going to be able to just switch from one feedstock to the next without having problems, because there will be different issues arising in terms of levels of contaminants. So a facility would have to test each feedstock individually or create mixtures of feedstocks that give you a homogeneous feed within the facility.
Okay. Next question we had was, what do you think about renewable power using at residue water hydrolysis FT?
Water hydrolysis FT, is that like a gasification or hydrothermal liquefaction? If you can just clarify that.
Hamid, I don't know if you want to maybe unmic yourself and clarify. If
Hello, do you hear
not,
me?
oh, yes.
Okay, good. Yes, actually, my question was about actually converting the ag residues, generating renewable power and then hydrolyze water to produce hydrogen
Oh,
and
yes.
then Fischer-Tropsch.
Well, I think it's all going to come down to the economics. And again, it depends on the scale that you can get as well. And if you're looking at ag residues, is the supply chain transporting the residues. It will be easier if you have some kind of a if you gasify in order to feed a boiler to generate electricity. The feedstock quality is less important than if you just gasify it to go straight to syngas, and the ag residues will be have less moisture and will be easier, I suppose, from a size point of view. The only issue with ag residues is the higher ash content, but certainly it's going to come down to the economics in my view.
Okay. The next one we had was, have you considered in-depth, smaller scale conversion processes to more closely meet the local forestry biomass supply challenge? FYI, the WBCEC-based, I'm assuming Northwestern Ontario smaller scale project recently completed its detailed feed study and business model.
Well, I'm not entirely sure what specific technology that is, but certainly, you know, either you transport the feedstock further, or you create some kind of I don't know if a SAF facility at very small scale has been shown to be economical. You know, the scale is obviously debatable, but at which point the economies of scale become really poor. That's kind of what we have to look at. But Fischer-Tropsch gasification, Fischer-Tropsch was developed with billions of liters scale. So I don't know if it's clear yet what is the smallest scale that you can go to, but even then transporting the feedstock is going to be a challenge. So densification can be a big option, important option. There are some studies, I think Professor Arno de Klerk at Calgary or Alberta University, they've done a comparison between a distributed feedstock supply chain and a direct feedstock to gasification. So there are some studies, but it's going to depend on the specific situation that you would have to calculate.
Next one here. Could you elaborate on production of SAF using end-of-life tires?
Yeah, so basically, end-of-life tires are usually not put into a normal landfill. So in fact, a lot of Western countries send it to developing countries, and then you can recycle it and produce carbon black, and there's also steel, of course. But you know, pyrolysis oil of end-of-life tires is actually quite a big thing. I think there are a few thousand pyrolysis facilities worldwide that do use tires. In India, for example, they burn it, which is bad because there's a lot of sulfur in it, but it is being started being used now for making fuel. Preem in Sweden, I think in the last month or two, started co-processing pyrolysis oil from end-of-life tires. The chemistry is better, it has less oxygen, but higher sulfur that has to be removed using hydrogen, but it's slightly easier than saying taking a wood pyrolysis oil.
Are VPPAs acceptable to allow low CI SAF production in, quote, dirty electricity locations?
Can you just, Keith, explain or define the VPPAs just so I make sure I know what you're talking about? Virtual power purchase agreement.
Virtual power purchase agreements. For example, if you wanted to build out a plant in Nova Scotia, taking in electricity from Newfoundland or Quebec, in order to not draw upon the Nova Scotia dirty power mix.
Well, that is a policy issue, because and we would have to look more closely at CORSIA. As I said, in the UK and the EU, it becomes very strict that the VPPAs is not going to be allowed to make SAF pretty soon. So it's gradually becoming stricter, that you would actually have to show by the hour that you are directly using the renewable electricity to make that hydrogen. But that's a policy decision. So different countries or regions could have different policies. Then CORSIA might have a different view on that. The actual methodology, the link that I gave you there, does have quite extensive information on the electricity source and how that all is calculated. I don't know that off the top of my head, but if you go take a look there for the CORSIA one.
Thank you.
Lots of questions. Okay, thank you all for your participation. Makes it so much more lively and entertaining. Most of the industries are producing SAF using ethanol. So can ethanol be converted? Ethanol can be converted to ethylene, and ethylene is a platform chemical. So why not make ethylene instead of SAF?
Yeah, of course you can make ethylene instead of SAF, but if you're starting with ethanol, then Canada is not the right place for you to be, because we actually have to import ethanol from the US in order to meet the blending obligations into the gasoline pool. So there is no excess ethanol produced in Canada. And yes, we can make it, but whoever is using the ethanol, it's just a economic viability issue. What's going to give you the biggest of income and profit?
Can you address how to tell the story of different feedstocks, example MSW and e-fuels from DAC? DOC have a great story. Fuels made from canola we grow, not so much. And then tallow using cows' bodies to fuel a jet, when we should all be eating less beef.
Yeah. Well, I think, we like to talk about the MSW and what I would call the more technically difficult feedstocks. We don't have those technologies commercial yet. What we do have is the HEFA process that is fully commercial and can produce SAF for us today. Yes, maybe we want to just use used cooking oil, but there's certainly not enough of that. When it comes to tallow, we are using the fats from animals, but mostly it's the inedible tallow where it can still be used for a food source. That is still done, but mostly they look at the inedible tallow that's actually not fit for human or animal consumption. So that, I think, is still a good waste. But the problem is that there's only about 30 to 40 million tons of waste fats and oils feedstocks available globally. So we are never going to be able to produce enough SAF if we just rely on the waste. And if we wait until we can gasify MSW and produce SAF, we might have to wait, I don't know, 5-10 years before we will get anywhere millions and millions of liters. So we're not going to meet 2050 targets if we only look at things like MSW. We have to look at feedstocks that we can use now and technologies that we can use now.
I am trying to reconcile the case that Canada has ample canola as a SAF feedstock. However, within CORSIA, it has an unfavorable CI score and requires sustainability certification. Why would an airline choose Canadian canola-based SAF over other pathways?
Well, when you start looking at large-scale facilities, it's obviously the accessibility and the certainty of your feedstock supply, and the canola industry in Canada, their actual pathway is probably far better than what the CORSIA defaults are showing. So the Canola Council and the Canola Oil Processing Association, they can show you that actually, based on very high yields, improvement of yields, that probably the ILOC value is much lower than what the default suggests. Plus, I think the individual canola producers in Canada, canola oil crushers, can probably demonstrate lower core values as well on a specific basis. So that is, I think, why it's still a useful feedstock.
Okay, and I see that we have about 1 minute left, so I think this will be the last question. Thank you for your amazing presentation. During your presentation, I heard you mention the role of crushing facilities in the canola to SAF supply chain. However, there's not much discussion about the refining stage required to produce SAF. Could you please comment on the current availability and capacity of refineries capable of processing canola oil into aviation grade SAF?
Canola oil as a oil can be used by the HEFA process, which is the hydrotreated esters and fatty acids process. This is fully commercial, but for the most part, companies have been producing renewable diesel rather than SAF, because there are actually two products that you can produce. And because there's a lot of favorable policies for diesel, incentives and so on, a lot of these producers, refineries, have actually just used the process to make renewable diesel. Currently, there is about 20 billion liters of capacity of these facilities, but there's, I think, less than 1 billion liters of SAF that is produced, and it's really a cost issue and a policy issue, because the policies give incentives to renewable diesel, but not necessarily to SAF. So a refiner says, okay, well, then I'm going to make renewable diesel rather than SAF, even though I can make them at the same time. The extra processing and so on that I have to do is more expensive, and it's not worth it. So really addressing the competition between those two products in order to increase the SAF fraction of the HEFA production capacity. As I said, 20 billion liters and growing, and we can produce a lot of SAF from that, maybe 50% even, if we have the right policies in place.
Excellent. Well, thank you so much, Susan, and thank you to everybody who joined today. If you are joining us tomorrow, we will see you tomorrow. And as I said, I noticed that some questions here were not answered. The ones related to C-SAF, I will follow up with you. And Susan can also follow up on some of the sustainability and feedstock questions. Thank you and have a good day.